Hello all, hope you're doing well. So in this lecture we are going to discuss about some additional topics of acid bases and salts. So first before moving ahead we are going to discuss about certain acids, certain oxy acids, specifically these: phosphoric acid, this is also called as orthophosphoric acid. So, what I want to discuss about these acids are the structures so that we can understand that why their basicity is different. Though I have discussed about acetic acid before also, like how we can actually figure that out, whether the bond involved oxygen and hydrogen, like whether it's oxygen hydrogen bonds, we have to see the polar bonds, and then whether hydrogen is bonded to the central atom, so considering as non-polar. So we are going to discuss three structures in this video. So in this phosphoric acid, the second one is H3PO3. This is called as phosphorus acid, and this is also called as orthophosphorus acid. And the third one that we are going to discuss is H3PO2. This is called as hypophosphorus acid. So first, since we have discussed about covalent bonding before, now this is slightly different, but if you know this slightly beforehand, then you'll be studying about these structures in redox reactions in depth later on. But at least you know you can have a fair idea before understanding those chapters. So let's start from this phosphoric acid. So we can see in phosphoric acid we have the central atom which is phosphorus. Now, I'm not discussing on the basis of SPDF, technically I should, but let's try to figure it out with the help of normal electronic configuration, KLMN. So, phosphorus atomic number is 15. So, we write 285 configuration. So we have five valence electrons. So first we need to figure it out when we have these kind of molecules. What is the central atom? So the central atom over here is phosphorus. So how many electrons over here do we have? Five. So we are going to distribute the electrons, which we have discussed before in the bonding part also, the electron dot structures. So if we have five, now I'll be drawing the electron dot and the line structures also. So line structure where I'm not going to show the electron dots. So phosphorus, H3PO4. Now if you see, so I've distributed these five electrons like this. First thing we need to remember, we need to be clear is that nothing in chemistry is hypothetical. It's all experimental. So we need to have a background information about these structures. You cannot, it's not like somebody got a dream and you got these structures, or you can just predict these structures. Sometimes, yes, like, if you don't know about the structure, so it can be a wild guess, but you need to have a background information how these structures are made. But yes, we can apply the logic, we can apply the concept, and then we can figure it out. Okay, this is how these structures are made. So now, coming to this phosphorus, so five valence electrons we have distributed over here, if you can see, and then we have three hydrogens and four oxygens. So let's try to see how we can, with oxygen, four oxygens are there. So obviously, I'm going to surround these four oxygens. So oxygen atomic number is 8, so 2 and 6 electronic configuration. So we have to show 6 valence electrons over here. So if you can see in this, you can say specifically these side oxygen, you can see only one electron is there for the bonding involved. So I'm showing only one electron, but we can actually do it like this. Here. So we have rest of the electrons. So if you can see, only one oxygen is over here, which is double covalent bond. So four oxygen atoms are done. Now we have only three hydrogens, if you can see. So hydrogen has a covalency of 1, atomic number is 1, so it can only share one electron. So over here also. So if you can see, this hydrogen is sharing one electron, forming a single covalent bond, and oxygen is forming two single covalent bonds, one with hydrogen and one with phosphorus. Similarly over here also, same thing, if you can see. Now what do we understand over here? The bond, there is no phosphorus hydrogen bond at all in this entire structure in phosphoric acid. We don't have it. We have three, you can say, OH bonds over here, if you can see, and these all three are polar. So polar meaning, that means if you dissolve this acid in water, so it's because this, the nature of this single covalent bond is polar, so it is going to be more reactive, it is easy to break, you can say that, and it's going to release three H positive ions or hydronium ions in the presence of water. So that makes the basicity of this acid as 3. Now we go to next acid of phosphorus. So we'll take H3PO3. So this is phosphorus acid. Now again, keep phosphorus in the middle. We know 5 valence electrons are there. Again, try to distribute like this. Then we have 3 oxygen. So 3 oxygen. Now if you can see, 3 hydrogens are also there, so oxygens are getting reduced in this molecule, if you can see. So same thing, so I'm not showing in the form of dot, electron dot. So let's try to understand with line structure. So we have, you can say, this single covalent bond, but valency of oxygen is not satisfied, at least for these two oxygens. If you can see, the top oxygen valency is satisfied because it's forming double covalent bond. So now we have our hydrogens left. So hydrogen is going to form single covalent bond with these and one direct single covalent bond with phosphorus. So now what you can see over here, there are two OH bonds. That means they are responsible for releasing the H positive or hydronium ions over here. And if you see, one bond is pH, which is non-polar, because the electronegativity difference or values of phosphorus and hydrogen are, you can say, almost similar only. So the difference is not higher. If you again go back to my previous classes about electronegativity, about polarity, I have explained this part in the covalent bonding. So you can check on my channel these videos, and you can listen to those videos for better understanding. So now these are polar. So obviously we'll be releasing two hydronium ions. So that makes the basicity of this acid as 2 and not 3. So you cannot say that it's always, if we have 3 hydrogens, so basicity is 3. Looking at it, so mostly you can say till 10th grade people have this mindset that it's like you can see from the structure, but sometimes you can see from the formula, but sometimes you have to see the structure in order to determine that whether the basicity is going to be 1, 2, 3, or whatsoever. So this is dibasic. Phosphorus acid is very much dibasic, and it's proved from the structure. Now we go to the third one, H3PO2, that is hypophosphorus acid. So in this again we are going to make the structure. So 5 valence electrons are not going to change, but we have only 2 oxygen, if you can say. So one oxygen I'm showing over here along with hydrogen, and rest of the hydrogens are bonded with phosphorus. So now if you can see, these are non-polar, but this bond is very much polar. So that makes only one hydrogen which can be released from this acid, making its basicity as 1. So if you haven't seen my previous videos, basicity is a number of replaceable H positive or hydronium ions which can be released from an acid when you dissolve it in water. So these three special cases I have taken. There are numerous examples of acids which I'm not going to discuss in this video, but yes, in later on in redox reactions we can discuss. Then we move to different theories of acids. Acids and bases. So I'll be trying to make this video shorter, hopefully. So we have already discussed Arrhenius' theories of acids and bases. Then we have second Bronsted and Lowry concept of acids and bases. Then the third one that we have is Lewis acids and Lewis theory of acids and bases. So we have already discussed about Arrhenius. Arrhenius defined acid and bases only in aqueous solutions. So if we go back before Arrhenius, it was Robert Boyle who defined acids and bases, like any substance which is having, you can say, sour taste, it is turning blue litmus to red, it liberate hydrogen when they react with metals, conduct electricity in aqueous solutions, neutralizes bases. So we define acids like that. Similarly, bases opposite of what I just said. So point over here is that Arrhenius only defined for aqueous solutions. So we have already defined what is an acid, what is a base according to Arrhenius. Acid is a substance which releases H positive or hydronium ions when an acid is dissolved in water. Base is a substance which can release OH negative ions when we dissolve it in water or aqueous solutions, you can say. But Arrhenius, you can say, fails to explain the acidic and basic behavior of non-aqueous solutions. So it cannot explain the acidic character of these molecules, like boron trifluoride is there, BF3, right? And basic character of these ammonia. Now, this is a problem. That's why now I want to say one thing. These theories are not correct or wrong. These are, you can say, defining different substances as acids and bases. They are not, we do have drawbacks. Obviously, every theory has a drawback, but we need to remember that they are defining large number of substances into acids and bases. So Arrhenius theory is defining for aqueous solutions. Bronsted is doing something else that we are going to define just in a couple of minutes. Then Lewis theory is defining on some different parameters. So they all are correct in somewhat manner for different kind of substances. So they are applying for different substances. So it's not correct or wrong. So now coming to Bronsted and Lowry concept of acids and bases. Now, I just want to change one thing. Let's not call it as theories. Let's call it as concept. Right? So I'm just going to change that. It doesn't fit. So if I'm talking about theory, so these are experimental proven. So I'm just going to change concept. Okay. So now Bronsted concept of acids and bases. So how do we define an acid according to this concept? So acid is particular substance which is which are nothing but proton donors. Now, please do not get confused. These are not protons which are sitting inside the nucleus of an atom. These are H positive ion. So we say H positive ion as a proton because if you see, hydrogen is the only element which is having zero neutron. If you remove one electron out of it, so the only thing which is left inside that hydrogen atom is a proton. So H plus ion is technically a proton which is residing in that atom of hydrogen. So proton donors to some other substance, right? Then bases are opposite of this proton acceptor. So obviously if they are going to donate, they are going to donate to some other substance. If they are going to accept, they are going to accept from other substance. So let's talk about this example, ammonia, right? Reacting with water. So we are taking an aqueous solution, but we need to prove that ammonia is a base over here. So this is our base, right? And over here, water is going to act as an acid. Water has a capability to act as an acid and base under different situations. So this is going to change into ammonium ion and OH minus ion. So if you can see ammonium ion, let's call this as acid 1, this is acid 2, and this is base 2. So what do you understand by this? See, ammonia is accepting, like water, if you split it up, H plus and OH negative ion. So water is donating OH negative ion, right? So if you can see that. So this, we are going to talk only about this ammonia. Ammonia is accepting H positive ions and changing into ammonium ion. So this is our base, this one is our acid base pair, and we call it as conjugate pair. So what do we say? We say, now if we have HCl as a gas, if we have ammonia, we have any other substance, right? So there are numerous examples under this. So what we need to understand is, if we don't have a solution, if we don't have an aqueous solution, this concept can help us understand that ammonia has a basic behavior. How do we got to know? Obviously by adding in water, but ammonia is basic in nature. It's a gas, but it is basic. And then water acting as an acid over here, water and OH is basically another acid base pair, and this is what we call as conjugate pair. So what do we say? Strong acids have weak conjugate base and vice versa. So you can take a base also. So whatever stronger part you have taken, if you have taken a weaker part, so the conjugate part will be strong. So it's always opposite. Weak acids will have strong conjugate bases. Strong acids have weak conjugate bases. Strong bases will have weak conjugate acids, right? Weak bases will have strong conjugate acids, like that. So now if we say, there are many examples, like perchloric acid is strongest, HCN is a weak acid, right? Hydroacid specifically weakest. Cesium hydroxide is the strongest base. So we can't basically say all the time. We need to see, because a particular acid, a strong acid, can show a strong strength in the presence of water, but we need to compare. And for comparison, it's not always the oxidation number. Sometimes we have to see other parameters, which I'll be teaching you in equilibrium chapter, not over here. So this, at least we can get an idea. So if we have HCl, right? So HCl changing into H plus and Cl minus. So what do you understand over here? HCl is donating H positive ion, if you can see that. So anything which donate NH positive ion is a acid. So what's a conjugate base over here? So the conjugate base over here is Cl minus. So these two are conjugate, you can say acid base pair. So since HCl is a strong acid, so Cl minus is going to be a weak conjugate base, like that. Then we go to the Lewis. Lewis concept of acids and bases. So Lewis acid is basically what? So it's a chemical substance which can accept a pair of electron. So we can take multiple examples. Aluminium trichloride. Now most of the time we say aluminium trichloride is a is a ionic compound. No, it's not. It's a covalent molecule. So again, we can have a discussion later on. So over here, there are multiple molecules. Aluminium trichloride is there, beryllium dichloride is there, magnesium chloride is there. So there are multiple examples. Over here, the central atoms have incomplete octet. See, even octet theory has drawbacks. So we can have central atoms as expanded as well as you can say incomplete octet. So incomplete octet means they are deficient. They haven't completed their octet, but still they do exist. That's a drawback. Now, if you go back to this one, I use the term expanded octet. See, when we have a covalent bond, don't you think that we, after sharing, what phosphorus is going to have? Like I said, phosphorus over here is having 5 electrons. So, what is happening after sharing? So, you just counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, after sharing, how many electrons do we have in phosphorus? We have 10 electrons. No doubt the third shell has the capability to accommodate 18 electrons. That's fine, but it is not an octet. It doesn't have 8 electrons in the outermost shell. It is 10 electrons, but still this molecule exists, and that's okay. Now again, we can actually explain this concept like why they are stable with the help of subshells, SPDF, d orbitals, and all that we can explain later. But these twists and turns, we should be ready in chemistry, right? For a lot of twists and turns. You can't say that okay, with one type of, you can say, rigid thinking, we can actually study chemistry. No, we have to open our mind. We have to be very much, you can say, flexible in order to understand chemistry. So, coming back to this part, so these molecules can actually accept a pair of electron. Now, the kind of examples, if you remember, if you have seen my videos of covalent bonding, I might have explained you dative bonding, the coordinate bond. So, ammonium ion. So, ammonium ion is getting formed between ammonia and H positive ion, right? So, H positive ion is a Lewis acid over there. Why? Because it can accept a pair of electron. Then one more condition we can actually say for Lewis acid, it should have incomplete octet, which I just wrote. So ammonia is basically what? Ammonia over there is acting as a Lewis base. Now what are Lewis bases? So opposite of what I wrote in the big in before this, it's a substance which can donate a pair of electron. So we have ammonia example, right? We can have any alcohol. So let's say methanol, right? We can have cyanide, ions also, Cl minus, OH minus, so many examples. Again, I'm skipping a little bit more examples out of it because that we can explain in the coordination compounds. So even coordination, okay, I have explained coordination compounds in my previous videos. So I can say I have explained in the types of salts, coordination complexes, specifically the ligands which I explained over there, act as Lewis bases. Now, what's the limitation for this? See, every concept has a limitation. Now, if you say Bronsted and Lowry, they don't talk about aqueous solution. Arrhenius talks about only aqueous solution. Lewis and the Bronsted and don't talk about aqua solutions, so you can say like that. So Lewis concept, it does not explain the behavior of protonic acids. Protonic acids are those which can release a proton, like HCl is there, sulfuric acid is there, nitric acid is there. Then does not predict the magnitude of relative strengths of acids and bases. So the golden line that we can remember, all Bronsted Lowry's acids are Lewis acids, while all Lewis acids need not be Bronsted acids. Bronsted Lowry acids. Why should forget that scientist name, right? Okay, so this was all for additional topics. So still there is pH left, normality is left. So in my next video, I'll be releasing about the concentrations except the normality. Normality I'll be teaching along with pH. See, there is a way to learn chemistry. I always say that. So I know, I cannot start directly from chemical bonding chapter. I cannot start directly from periodic classification or from subshells. Just like if you're making something, you need to create a base. So we are creating base over here. So because of this lack of base, most of the people don't excel in chemistry and they end up just mugging, just carefree mugging. I've seen, just they don't have any background knowledge of so many things and they just learn, they try to pass so many things, and sometimes they fail also, and that's okay. Failure is one step to your success, that's fine. So that's all. So I hope you have understood this video, and you'll be watching all the videos which are required previously. You can go to my channel, you can search over there, and I'll be uploading the concentration videos also soon. So thank you for listening. Please subscribe my channel and share this video to your friends, whoever is requiring this kind of help. Thank you.